Okay, so before we go into detail on measurement variance and multi-group testing, we need to make one adjustment to the modeling framework that we've been using so far, and that is that we're going to add the means. So what does that mean? We're going to add a intercept factor and a mean factor to our model. So here we have our model. Now we're adding this tau here, and now we're explicitly modeling this mean factor of the observed variables. So previously we did not, we ignored it, and that was comparable by saying, okay, we just assume this has a zero mean, for example, and that all the data are centered. And actually it doesn't matter for the covariance structure at all, so we can just input the covariance structure in the software and then it went fine, and then we can do that. An alternative would be to say, okay, the means are just the means of the data and it's not really that interesting. But now we're going to explicitly model this as well. And also at the latent level, we're going to model the mean of the latent level. So that means that our latent variable is no longer centered around 0, but it could be, for example, centered around something else called alpha. The residuals still have a mean of 0 because we don't assume any structured bias. So we assume that the error will be random, but not structurally, like always one higher or something. So we're adding this tau here, which is an intercept factor, and sometimes, quite often actually, this is called nu. Also in psychokinetic software it's called nu. But I'll use tau in the slides. And we're going to add this alpha, which is a factor of the latent mean. So those are two more parameter factors that we're adding to the model. And now we have the model, and that becomes a model for the variance structure and for the mean structure, because we have both here in the big model for y. So the variance structure we already had, this is the same. This is sigma equals lambda psi lambda transpose plus theta. But now we can also compute an implied structure for the means. So this model here implies this mean factor here. And that's using expectation algebra. In SEM 2, in the first week, we'll learn how you can do this yourself and see that this is true. But for now, you can just assume this is true. So if this is the model that generates the data, then the expected means should have this form, tau plus lambda times alpha. Now, in our fit, we wanted S to be as closely as possible to sigma, right? Or actually sigma as close as possible to S. And now we also want the observed means, let's call them y bar, the sample means, to be as closely as possible to this mu that we're modeling. And we need to put it in the fit function. So we have the fit function here, and then we add this part here. Now I have a video on the fit function where I did not add the mean structure yet. But basically you can roughly take the same steps. At some point it becomes a little bit more complicated because you have to add this y bar in there somewhere. But then you can derive the same formula. So this fit function is the same interpretation as before. And what we could also see before is that we just assumed that mu and y bar were 0, for example, if we had centering. Or we assumed that they were the same. In any case, this thing just became 0. So then this drops out and this drops out, right? But we don't assume it's 0 now, so I'm gonna, so then it doesn't drop out. And then we have this added term, which is related to this mean structure. Okay, so we have an extra added parameter vector, and we also are now modeling the means. So that means that our number of observations is a bit larger now. So we had p times p plus 1 divided by 2 variances and covariances. Those were the unique entries in this S matrix. So we have like a lower diagonal here, and the number of elements here, 1, 2, 3, 4, 5, 6, 7, etc., etc., etc. That's resulted to p times p plus 1 divided by 2. But now we're adding p means. because we're also modeling the mean vector y bar, which is also put in our model, and this is also things we put in the optimizer, so we have more information actually. So instead now we have p times p plus 3 divided by 2 number of observations, right? And that is the same as p times p plus 1 divided by 2 plus p. Okay, so you can read this p divided by 2, 2p divided by 2, and then that becomes this plus 3. But we also have added some parameters. We have added p-intercepts in tau, and we added a latent mean for every latent variable we have in alpha. Okay, and now we have one more problem, and that's an identification problem. So what we first saw already with the, let's say, the vector model here, is that we had to scale one vector loading or the variance coverage made, or the variance, of the latent variable to 1 to identify the scale. And that was to have this distribution of the latent variable. We needed to set this width of the distribution somehow, because it's latent and we don't know it. Now we also need to put the location of the latent variable, because we need to set the mean of the latent variable because it's latent and we don't know it. Right, so a latent variable might have a mean of 0, it might have a mean of 100, we don't know. Right, if it has a mean of 100, then these thresholds will, these intercepts will just be lower. If it has a mean of minus 100, these intercepts will be higher. Right, so this alpha and these intercepts can actually cancel each other out. So we have an identification problem, right? We can arbitrarily set alpha to any number and then adjust the intercept so that we have the same mu. And actually we can already see immediately a problem here in this equation. If we write this out, we have mu, which is a vector, let's say, of 3 variables. So this is 3 elements, equals tau, which is a vector of, let's say, 3 elements, plus then lambda alpha. So let's say we have one latent variable, right? So then we have lambda is also just a vector of 3 elements times one latent mean. Okay. Now this one we already have in the expression for sigma as well, so there's no identification problem in there. But what we see here now is we have here 3 unique elements, 1, 2, 3, and here we have 1, 2, 3, 4 parameters for the mean structure, plus this stuff in lambda, but that's already also identified in sigma. But 4 is higher than 3, so that's a problem, so we're over-identifying this model. So we need to put some constraint in here to have the same number of parameters at least, because otherwise for the mean structure we would not have degrees of freedom. So what we do is we actually remove this latent mean. So we need to just simply identify this and also put this to an arbitrary value. Just like we said c is 1 or lambda 1 is 1, we also need to identify this latent mean, and we can say alpha equals 0. So then if we set alpha equals 0, we're left with p extra parameters, because we have only this tau. And we also have p extra observations, so degrees of freedom is still the number of observations minus the number of parameters. And that actually won't change, because this is just plus p and this is just minus p. Or also plus p, but then minus that. So nothing changed. So this whole thing seems a bit arbitrary, right? So because it's alpha, we set to 0 because we need to identify it. So if we add the mean structure, we just add p more parameters, but also p more observations. Turns out that this tau will then, so this is 0, right? So this is gone. So we just have mu equals tau. Well, we can already set that before. So then tau is sample means, and then mu will exactly equal the sample means. And then we're done. So that's why we can ignore the mean structure normally. Okay. So what does this look like? Well, here I have a path diagram like we had before. Okay, so we have one latent variable. I scaled here the vector variance to 1. Now we have residuals here, things like that. Now we're going to add a mean structure. And one way you can draw that is by having this triangle, which represents a constant, right? Because an intercept is a regression on 1, right? So let's go back to the previous slide. So here you can see this is times 1. That's the idea. A bit silly, but that's the idea. So one way to draw it is by adding a constant term 1 and then saying, okay, so these are regressions on 1. That's the way I'll draw them in these slides, but there are other ways that people draw an intercept. Sometimes they draw like a little diamond or something like that. Okay, so here we added 3 intercepts. Now we need to take the means as well into account when counting the number of observations, so we also have 3 more observations. And then we have a latent mean, but that's identified to be 0. And that's it. So that's adding the mean structure. Now this doesn't change anything for anything you've learned so far. But now for the rest of this video series, we'll see examples of where this will be useful.